So what we're going to talk about today is HardenedBSD. We're going to start out with a bit of an egotistical moment as people file in, and then we will dig in. This presentation is going to be a choose your own presentation, choose your own adventure. What I'm going to do is I'm going to talk a little bit about HardenedBSD, what we are, who we are. I'm going to give a very brief introduction to our features, and then I'm going to ask for each feature a raise of hands, and you guys will be able to vote about which feature you guys want me to talk about. I've got 4 hours worth of material to cover in about 50 minutes, so this is going to be exciting. So I'm the co-founder of HardenedBSD, and I'm a big security enthusiast. I was introduced into the security industry, the underground security world, as a teenager, and I just fell in love with writing buffer overflow exploits and a lot of low-level stuff. These days, I'm more focused on the defensive side, and having that offensive side as a base gives me a lot of good insight as to what kinds of things we want to do in HardenedBSD as defensive measures. I'm a big advocate of open source. I owe my whole life to the open source movement. The people sharing their code and allowing me to learn off of other people's hard work has changed my life around completely. And I admire anyone who publishes any open source code, even if it's something as bad as systemd. I admire that someone's still putting out the work to write atrocities. I love FreeBSD, and I love the other BSDs as well, but especially FreeBSD because of especially the things that Alan Jude talked about, ZFS. It's been a lifesaver as well in my professional career. In all things, I consider myself a noob. I'm learning new things every day. You'll see me post in IRC, newbie question alert. That usually means I'm too lazy to look at a man page. And there's always something new to learn every day. And I figure might as well call myself a noob because I'm a noob. So security. What is security? It's what Sony, Mt. Gox, Ashley Madison, and now OkCupid all have in common. They suck at it. Security really is a layer. It's multiple layers that make up of an onion of sorts. The more layers you have, the more layers an attacker has to peel off in order to successfully exploit a given vulnerability. At no point do we in HardenedBSD claim that a single layer is the end-all be-all measure of security. We believe in making life difficult and pissing off the bad guys. And so that's our aim, is to implement more and more layers so that an attacker is frustrated beyond belief and may even give up. So these layers that we're implementing in HardenedBSD are called exploit mitigations. And you can see they're cutting back the onion. They're cutting back those layers in such a secure fashion. An example of one such layer, of one such exploit mitigation, is something that we are known pretty well for, and that is address-based layout randomization, ASLR. So a little bit about HardenedBSD. We're still small time. We're still small time, but we're making a big impact. There's a lot of companies that are looking into us, and in fact, I have a surprise announcement today. And for example, we recognize that even Sony is looking into us, maybe for their next PlayStation. And officially, we launched last year in April of 2014. And we launched, we pretty much did exactly what NetBSD. It's not a fork, but it's a spork. We actually sync with FreeBSD upstream every 6 hours. And so it's not like we're doing all these customizations and we're never going to push them back, and it's going to be a nightmare to maintain these. We actually, we did this because we launched and forked the code base because it was really difficult, and it still is to this day, to try to upstream these things, these projects like ASLR. We're 2 years into the upstream process, and we've yet to get a single patch in regards to ASLR. So this is kind of difficult, and so we wanted to unify our efforts and make it make it a whole lot more simple on our end for us. When we first started, both Oliver and I, Oliver is the other co-founder, he lives in Hungary, and we were doing ASLR development in separate repos and trying to coordinate our work that way. And so we wanted just a single repository for not just ASLR, but for further development. We'd always make sure to test our code on different architectures, on 32-bit Intel, on 64-bit Intel, on ARM, and now, just recently, I've been testing on ARM64, on the QEMU side of things. And I should have a physical ARM64 appliance coming within the next month or so. I'm really hoping it has to pass the FCC. I've already paid for the device, but the manufacturer has to pass FCC requirements. So we have a few different contributors, 5 developers, and 3 of which are active today. We added our third official developer just a few weeks ago, maybe a month or 2 ago actually, and he's tasked on working on rewriting one of our little projects that helps administer the security of HardenedBSD and the features of it. We've had a few contributions from universities. We're working with one contribution from, I don't remember the name of the university right offhand, but it is Nathan Downhan's work. So for the memory separation. So we have a 3-year game plan, and this actually is in the process of being molded and sculpted every day. We want to upstream our projects like ASLR and like NoExec and a few other things. We would love to set up a not-for-profit organization so that any donations that come in are tax deductible. And we're in a catch-22 situation. We need donations in order to have the money in order to tell the IRS we need money. But those donations aren't tax deductible. And so in order for further donations to be tax deductible, we need donations. We want official releases. That's going to happen next year. Official releases will happen next year, starting with 11.0. Right now, we're just doing nightly builds. We do not provide binary updates outside of our package repository. Once package base is in a testable state for us, we will investigate using package base for the base in the kernel and provide binary updates that route. We want to provide commercial support so that if you have a problem with an appliance you're running HardenedBSD on, that you can call us and we'll support you. We want a for-profit arm to sell things like hardware appliances like firewalls and intrusion detection systems and prevention systems. Oliver would like a nice little GUI tool that you can use to administer HardenedBSD nodes on your network. So this is an interesting topic. I get asked this a lot, is what's up with OPNsense? What are you guys doing with them? Well, what we did is I have this ASUS wireless router at home, and we all know and love their vulnerabilities. There was a 1-month period where my specific model of router, a 30-day period, had like 3 or 4 different remote root vulnerabilities. And since I'm running HardenedBSD infrastructure, the package building server out of my home, I'm like, I don't think I want my vulnerable ASUS router to be my edge gateway. And so we ended up working with OPNsense, and we are now in the process, we've teamed up with them, and we are doing experimental builds right now. And soon, very, very soon, within the next month or two, those experimental builds will stop being experimental. They will have a binary upgrade path, and they will be full production-ready releases. And I am using OPNsense based on HardenedBSD in production today, both at work and at home. We have actual appliances at work that we are going to start developing. And that's pretty cool. This is really awesome. I love it. So today, I have a surprise announcement. Zenuous has genuinely decided to contribute a sizable contribution to HardenedBSD. Our hardware, the building packages is pretty stressful on hardware, and we need to replace some components. The motherboard started failing. The CPU pinouts, the CPU fan pinouts actually just stopped working entirely. So I had to put the CPU fan on a backup pinout. And so we need a little bit of help. We needed some support. You know, critical pieces of the internet infrastructure are running FreeBSD. And we need these expert exploit mitigation technologies to secure the internet. You know, this is my way of saying screw you, NSA. And if we can get funding, I'm not trying to plead with you guys here, I'm not trying to grovel, but if we get more funding, that's going to allow us to do more things and to help secure the internet. It'll give us more time, more resources. Instead of taking about 8 days to build one package repo and sync it up with our repositories, we want about 2 to 3 days. And that takes a chunk of time out of my day to administer that. So I'm really grateful for Zenuous to donate quite the substantial amount. And I really look forward to working with them in the future. So these are our features. We have ASLR, of course. That's what we're known for. And our version of ASLR, we like to think is the strongest form ever implemented in the BSDs today. There's a lot of cool things that we're doing. We've tied in map 32-bit on 64-bit platforms. You can tell the memory manager to force a certain memory mapping to be within 32 gig address space. And so we have now the ability to toggle that, to allow that or disallow that. We have what is called noexec. The NetBSD guys and OpenBSD guys like to call it WX or X. We like to call it noexec because that's what PAX, the PAX team, termed it as back in the day. So it's actually a combination of a few different types of technologies, noexec and pageexec. But they're kind of synonymous. They go hand in hand. So I'm going to call it just noexec in this presentation. So we have protections on Lin procfs. There's a pretty interesting vulnerability that happened like a year or so ago that an exploit author, they were able to control SFT. So if you give a user only the ability to SFTP in, so they can't actually SSH in, they can only transfer files via SSH through the SFTP protocol, they can actually abuse procfs to change the process virtual memory address space and force it to drop them into a shell just when they're transferring a file. That's a pretty cool attack vector. We've closed that. And ptrace is pretty cool. It allows you to be God It allows you to change, just like the procfs restrictions, it allows you to change the process address space and the contents and how the process works. So we've restricted that quite a bit. We've removed completely the ability to map at null. So you can't map at the 0 address in HardenedBSD. That's not even possible. So null dereference vulnerabilities are simply just access violations, segmentation faults. You cannot get, you cannot map at null and execute arbitrary code there. We've removed many of the old image activators, like a.out, and we implemented get entropy. We ported that over from OPNBSD, and we have some boot hardening things like enforcing sbin init forcing the kernel to truly only execute sbin init. We also have seg vguard in HardenedBSD, and we're in the process of making that more efficient and fixing a few bugs with that. And we think we're done with that, and we think it's production ready. Oliver, in last year, I think it was, he implemented smap under a Google Summer of Code project. I don't think that ever made it upstream to FreeBSD, and that is in a broken state right now, but we are going to be working on it quite soon. We have the SecADM, Security Administration Project, or application, that allows you to toggle on a per binary basis all of these features. So, for example, Chrome and Firefox don't really work right when they have no exec applied to them. So you can say, for this application, disable no exec protection on them. We also have a feature inside of SecADM called Integriforce. It's kind of like NetBSD's verified exec. It enforces file integrity. It makes sure that the hash that you have of a given file that you stored in a configuration file matches when you try to execute that application. So there is a lot that has changed with ASLR. There's a lot that we've done. And some of it is quite complicated. Some of it is, let's see. So first and foremost, what? Oh, that's because I'm on my work laptop. Forgot to actually SSH. So let's do this. There we go. So I'm going to start with our header real quick. So what we did is we have this structure called the hardening features structure. And this structure contains all the per jail settings for our different features. You'll see at the top, we have PAX ASLR status that says whether we are disabled, whether applications whether you have to opt in applications via SecADM, whether you have to opt out applications with SecADM, or whether ASLR is enforced globally. So there's four different settings just for the status. We apply different deltas. So what we do is when an application is about to be executed, we generate 4 different deltas. One for the mmap base, one for the stack, and actually 2 for the stack, but these are the settings about how many bits of entropy to introduce into these deltas. So stack and the executable base for position independent executables, and the VDSO, or the shared object, or the shared page rather. So what we did is also in jail.h. So in jail.h, in the kernel part of it, we add that structure. So every feature that we have in HardenedBSD can be toggled on a per jail basis, and additionally a per application basis for your applications running in jails. This is actually pretty cool because even the host is a jail. So even your host OS that runs all your child jails itself is a jail with all permissions set to it, so it can do anything it wants. So we're going to go to the HardenedBSD specific code. Actually, no, we need to go back to the headers. It is It's going to be process. Yeah. There we go. So what we did is there's a few variables in FreeBSD's source code that are hard-coded. They are architecture-specific variables that say where the stack starts, where the user starts using the stack, where the end user application starts utilizing the stack, and where the shared page is, if that architecture uses a shared page, and where the signal trampolining code is, which is generally on the stack or in the shared page. On a lot of architectures today, not all architectures, but on a lot of them. So one of the things that we had to do, and this is kind of a big diff that I'm going to collapse into just a generalization, is we took all those places where we are referencing PS strings, that macro, it's all uppercase, and we made it pretty much per process because we're going to apply the delta to the stack. We are the only BSD OS that uses true stack randomization. Everyone else, including OPNBSD, uses just a gap on the stack. So that means that the stack starts at the same point, at the same address all the time, and where the application starts using this stack changes. Well, what we did in HardenedBSD, and that's part of the per process change that we did, was the stack actually starts at a random address, and additionally, we apply a random gap to that. So we can actually introduce 42 bits of entropy into the stack address, which is pretty cool. That is the highest. I believe that, no, I'm not going to say that. I don't want to say something that I can't confirm right offhand, so that I suspect to be true, but I can't confirm it right now. So, so what we're going to do now is we are going to go into HardenedBSD's main code. And in here, we have strings that say how that feature is enabled or disabled. So, you know, if the feature is disabled, this code is shared among all of our features. So like with the no exec and ASLR, we don't want to rewrite common things. And so this shows us the status of how they're enabled. And this procfs function. So when an application starts up, it's going to initialize its flags to say ASLR is enabled or disabled, no exec is enabled or disabled. So this procfs function is what initializes the state of those flags when a process starts up. So we go through and we validate that the requested mode, that the requested flags are valid, and we make sure more validity checking, sanity checking, and we set the flags for ASLR, and the map 32-bit protection ties into ASLR as well. So there's the flags for no exec, and the flags for SEG vguard and our generic hardening features. And we go ahead and we revalidate the new flags. So after attempting to set the flags on a per feature basis, we now go ahead and validate what we've attempted to set. And then we go ahead and set it. And then if the process, if like secadm, for example, said, let's disable, even though ASLR is enabled for the system, but let's disable it for this application, we'll print out an error message or a warning message on the console that says, hey, this application was set with non-default settings. Make sure that this is correct. Just in case an attacker was able to disable something. We have some sort of auditing infrastructure there. So again, we have the ability to set our features on a per prison basis. And so this init prison does that. It sets up inheriting. So if you have ASLR disabled in your host jail, in the host, when you start up a new jail, it's actually going to inherit those settings. So that jail is going to start up with ASLR disabled as well. What you can do then is inside the jail after boot up, if you decide to do this, you can enable ASLR in that jail. And if that jail can create its own sub-jail, so now you're 3 layers deep, that jail will inherit the parent jail. So that jail will start up with ASLR enabled. And remember, the host OS, the host is still disabled, but the 2 jails now have ASLR enabled. So this is where the magic happens with ASLR. At the top, we have a lot of ASLR specific. We didn't want to have our macros that are specific to ASLR in a separate include, because we might as well just have them here and not bloat the includes. So we have some macros and some defaults here. So we set the minimum, there's a minimum number of entropy that you can introduce and a maximum number of entropy you can introduce for mmap, stack, exec base, and VDSO. So this is pretty much setting those macros. And we set the defaults for those. And those defaults we like to keep pretty high. So we also have, you can set those at boot time or at runtime. And we've architected it so that if secure level is set, you can't modify these tunables, these system controls. They're implemented as procedures, as full-on functions. So it's not just setting an int. We actually do validation on each of these tunables. So we make sure that that the value that they passed in through that sys control is valid. If they're trying to set the status, whether the feature is enabled, disabled, opt-in, opt-out, we make sure that what they pass in is valid, that kind of thing. And same thing with mmap. We make sure that it's within the minimum and the maximum range of entropy that we allow to be introduced. And same thing with the stack. And same thing with the exec base and the VDSO. We have different settings for the compat layers, so compat FreeBSD 32, compat Linux 32. You can't randomize as many bits on 32-bit as you can on 64-bit. So we actually have to have different tunables for compat versus non-compat. These tunables are only exposed as sysctls during runtime, post-boot, if you have a special option set in your configuration file. Otherwise, you can only set them at boot time, or just leave them as their defaults. So we have the exact same thing with the compatibility layer as we do with the non-compat, the native layer. And this is the code for the map 32-bit disabling. And here is for our features, we have to have a sysinit. So at boot time, we make sure that the values you place in loader.conf or loader.conf.local make sense. So we do some sanity checking there. And if they don't make sense, then we print out a warning and we force it to our highest security state. So if you set the status, for example, the activation mode to 5 when you can only set it to 0 through 3, then we're going to actually set it to force enable ASLR for all applications. Then we print out some debugging info. And then we continue on with the map 32-bit stuff. So this packs ASLR active function, what it does is it checks to make sure that the per process flags, it just checks to see whether ASLR is enabled or disabled. If there's an invalid mode set, then we force it to be enabled. It's pretty simple stuff. We've abstracted this out so the code is really easy to read, but there's a lot of code. Here we are initializing the VM space. So this is where we are generating all the deltas. When the process is being created, when you're in the exec VE land, not in fork land, but exec VE, this is where we initialize our deltas. So we call into arc4 random, actually. We grab entropy from the randomness provider. And that actually is now causing problems with us with Mark M's latest changes to the randomness provider. Because at boot time in VMs, and especially Beehive VMs, we're seeing that not enough entropy is available at boot time unless the boot entropy file exists. So if you're trying to install HardenedBSD into a VM, especially like Beehive, where there isn't much I/O activity involved, there's not much jitter going on to generate entropy, to fill the pool with entropy, then you can experience some interesting behavior. We are currently working on fixing that. There are still some issues. We've fixed it for the most part, but there are still some lingering issues. And that's due to a change in upstream code that has affected us. It's kind of a cool bug to happen, but it's a challenging one to solve because crypto is hard. I didn't know that, but crypto's hard. So here we are generating the randomness according to the settings that you've set. I've set, for the mmap base, we'll say grab and introduce X number of bits of entropy into the mmap base. So here we go. There's a stability fix. Here's part of the workaround for these randomness provider changes. This is actually dealing with the VDSO. That the VDSO actually has to start and end between the stack, the top of the stack, and the bottom of the kernel address space. So there isn't much randomization going on between the stack and the VDSO, but the VDSO cannot start after the stack, or I guess at a lower address than the stack, and it cannot start at an address higher than the start of the kernel address space. So we actually had to provide a workaround, a stability fix for that. And we print out, we provide KTR debugging right now, and we will, for the FreeBSD upstream patch that we have, that we're reworking, we will be using dtrace. Robert Watson has asked us to, instead of using KTR, these CTR2 functions, which are actually KTR, the feature is called KTR, he wants us to use dtrace. And so we will be working with that. I think in HardenedBSD, we're going to stay with the KTR because it actually works at a lower level that fits our use case better. So we're doing the same thing with the compatibility layer. We have to initialize the deltas as well for the compat layer. So we've actually abstracted things out in the sysentVec. We had to add an entry in the sysentVec to say this is how you initialize ASLR for this process, whether it's a 32-bit process or a 64-bit process. Those deltas, like I said, there's two different types of deltas. There's the native host architecture and the compat layer. If you're running 64-bit, chances are you have the compat layer enabled as well. So here's where we initialize the per prison stuff for ASLR itself. So prison 0 has no parent, that's the host. And so we actually have to do this kind of really long conditional statement to detect whether we're in the parent, the host, or whether we're in a child jail. So it's kind of, I don't really like that code, but it's got to be that way. So here we are applying the delta to mmap. When mmap is called, we only apply the delta when we are not requested a fixed mapping. So if the application requests that mapping be placed at a certain address, then we don't modify that at all. Because it's requesting a certain address, ASLR cannot be applied there. So we have some documentation here. We point over to the PAX docs. Here we are actually applying, after some sanity check-ins, that delta. We also randomize the runtime linker. So previously, the runtime linker actually, the RTLD, gets loaded at a fixed address as well. And we can apply, because it's just a shared object, it's not an actual application. Since it's a shared object, we actually apply the same mmap delta to that as well. Here is the awesomeness of where we are applying the stack delta. We have to tread lightly here because the stack is pretty fragile work. There's a lot that gets placed onto the stack. So we have the top of the stack right here, and at the very beginning, it isn't your argv and argc and environment variables. It is an auxiliary vector that the runtime linker actually uses. And then below that, on some architectures, is your signal trampolining code. And below that, on some architectures, is your timekeeping code. I could be wrong on the timekeeping code. But I think there is one architecture that does have that on the stack. I think that might be ARM. I could be wrong. So there's more data that's on the stack than just your argument variables and environment variables. So we have to actually do some fix-ups. First and foremost, we apply the delta to the stack itself, to the top of the stack. And in the next function, we apply the gap. So we have now, in the first function, we've applied the delta to where the stack starts, and this function applies the gap, and that allows us to introduce further entropy than we would be able to introduce otherwise, because the stack actually has to be the stack top can only be randomized on a per page basis. So that's a 4K page on 32-bit, and I think on 64-bit as well. Yes, 64-bit is 4K page, on AMD 64 rather. So having the gap allows us to, instead of just page level granularity, it allows us to go down to having a 4-byte granularity. So we can start an 8-byte on 64-bit. So pretty good stuff there. We are the only BSD that does it like this, that does the true stack randomization with a gap. So this is pretty easy stuff, applying the delta for the executive base for position-independent executables, and doing the same thing for the VDSO. And we are setting up the flags. So these are the per process flags. We also have a feature with ASLR that we also randomize the loading of the shared objects. We kind of do what OpenBSD does. Our inspiration for that was actually OpenBSD, that we can randomize the order in which shared objects get loaded in for a given application. So these are just setting the flags. It's pretty easy stuff. So if the requested flags for that application don't make sense, then we force ASLR to be on, and we force the shared library randomization to be on as well. So these are the same things, but except for 32-bit for the compat layer. So pretty simple stuff. So that is that file. Let's go into the kernel now. How am I doing on time? 20 minutes? 10 minutes, okay. So PAX, ASLR. So here in, where are we? Do exec VE, when we actually try to execute a new application, the first thing that we do is we try to initialize the stack, the gap. And then we initialize the flags, later flag, actually not the flags. We initialize the image args, image params structure. And then we go ahead and if a shared page, if a VDSO exists for that platform, we go ahead and randomize that. This is just logging that we didn't succeed in randomizing the shared page, which doesn't really happen. We just have that there for some initial debugging purposes. We can remove that. Here we are randomizing the stack top. This is all in do exec VE, by the way. This is a pretty large function. And more VDSO randomization. We have to apply the randomization to the SIG code base, since the SIG code on those architectures that have a VDSO, the SIG code is actually placed in the VDSO, so we have to fix that up. And there we go. There was I believe. Okay. Let's see. So if you experience a kernel crash and you go into DDB, then you can show the ASLR settings for that jail. Let's see. So that is as much as I have time to show you today. There's more stuff to do, especially with the changing from PS strings and stuff to the per process, things like that. Working on re-implementing our upstreaming patch. So we're taking our big, long review, existing review on Fabricator that's existed for longer than 2 years, and we're shrinking that down to little bite-sized pieces. I'm still hungry. And I love Hawaiian pizza. So we're re-implementing that big patch as bite-sized pieces so that it's easier to digest. So there's a lot of work that has been done in just the past year. We've done a lot. We've completed our ASLR implementation. The technical details of it are 100% complete. But there's still a lot of work to do in HardenedBSD. We are going to be finishing up page exec and no exec here, hopefully within the next month to 2 months. And our overarching theme, our first goal is to port over all of the features in GR Security, which is a third-party patch for the Linux kernel that hardens both the kernel and the userland. We're going to port over all of those features that make sense for HardenedBSD over to HardenedBSD. We've learned, and the InfoSec industry in general has learned that if you combine multiple exploitation mitigation technologies, you're going to have some pretty good security. You know, there is no end-all be-all of security technologies. There's not a single security technology that's going to save you. At some point of time, you're going to end up like Sony. You're going to be pwned. But you might as well make it harder for your attackers. You might as well make them spend more time and resources to attacking you than otherwise. Our next milestones is, for the short term, is we're going to have official OPNsense and HardenedBSD builds. And the OPNsense team is actually working on importing our work. And we are in the process of completely rewriting SecADM and making it more efficient. And in that rewrite, we're actually going to have a UJIT-FW, full-on UJIT-FW replacement. And later on, I think after that, we're going to also include GRSec RBAC type of facility as well. We want to do UDREF as well. That is pretty cool. That makes it so that kernel code cannot directly access user data. And one of the things that we want to look into is ELF code signing. That will replace our Integriforce feature. We also will have an official release next year. So these are some links that you can go to. So do I have any questions? Yes.
So is all your randomization just from kernel space, or have you looked at userland malloc stuff to further randomize where heap allocs are placed?
Yes, that is a great question. So the question is does all the randomization for the userland happen in the kernel, or is there additional randomization in the userland for the userland that happens in the userland? For example, the heap, the malloc implementation. FreeBSD uses JE-malloc, and they recently imported JE-malloc 4.0, I think is what it is, the most recent version of JE-malloc. And that JE-malloc detects whether your system uses SBRK and will default to using SBRK for the heap. And that actually presents some issues. So we are actually investigating right now, actively investigating. We've got a ports run that is happening to tell JE-malloc to force JE-malloc to using mmap. And that will tell JE-malloc to create anonymous memory mappings that we can randomize. And so with SBRK, that presents some challenges in randomization. If we force JE-malloc to use anonymous memory mappings, then yes, we can apply ASLR to the memory allocator. So that is in process. We're testing that right now.
I'll find you out.
Okay. Any other questions? That was a great question, by the way. Thank you. There are more things that we do need to research, especially with malloc, with JE malloc, but that is where we are starting with. If you have a follow-up question, feel free. Sorry,
because it's not just like, oh, hey, we're using malloc, so we're going to have randomized addresses just from where allocations are placed. But there's also, at OpenBSD, we've randomized stuff within pages, so it's not just that 12-bit granularity, but you have like, a little while ago, to what extent it benefits, but we've had like multiple free lists, and you have some non-determinism within your userland malloc. So it's, never mind, I'll find you after.
No, that's a great question. We will be looking into that, but we are starting with the basics first. It's just Oliver and me, so we have to go line by line, precept on precept, and so we're starting with the first forcing JE malloc to use mmap rather than SBRK. So did you have another question?
No, I had a question.
Or a question, sorry.
Yeah.
Another question to me.
I find it interesting that you're, I haven't seen the word prison used before.
Mm-hmm.
And so now you're using jail. I mean, if you keep adding these, you're eventually going to have to start naming prisons like Sing Sing and Alcatraz. I thought that would be kind of interesting.
I can't really hear you. Can you step to the mic, please?
I was just making a joke.
Oh.
But I enjoyed your presentation.
Oh, thank you.
I thought you didn't repeat the same word like 50 times and over the course of several slides, so I enjoyed that. But this was really technical, and I don't know how you're going to do stack randomization. I think that's kind of interesting. But I just wanted to say that of the ones I've seen, we've kind of gotten better as we've gone on. I really appreciate all of the presentations, but I think this one has been really great. I just wanted to say thank you.
Well, thank you. I appreciate it. Any question? Any other questions?
Hi, Shawn. Thanks again for the presentation.
Hi.
I do have a question. Have you observed any kind of functionality issues with userland when introducing these features? I have in mind in particular wine, because I believe if you deny wine the possibility to deref null pointers, it would actually not work anymore. So have you observed this or any other piece of software breaking with ASLR?
So we have experienced some anomalies, not complete breakage. So with ASLR, for example, we have the shared library randomization, and there are some applications that misbehave with that. Privoxy, for example, expects that libpcre is loaded in a specific order. It depends on quite a few shared objects, but it expects libpcre to be loaded before or after a certain other shared object. It doesn't matter where it's loaded, just that it's loaded in a certain order. And that is why we actually have the shared library randomization order toggling on a per application basis. We hope to work with these third-party projects to fix that upstream so that we can actually get rid of this workaround on our end. But there are some applications like Privoxy that do that. I have not experienced for things like ASLR and the mmap null dereference features. I have not experienced full-on crashes with applications.
I'm also curious about Firefox, because I think to optimize JavaScript, they have to generate code on the fly and limit it to like 32-bit address space within a 64-bit port. So did you have anything special here to handle that?
Yep. So so that's where NoExec comes into play with applications that use some sort of JIT like Firefox and Chrome and V8 and Node and some other applications. And Java is a big one. and there's like 20 different applications in Java that all. So we are able to toggle those features on a per application basis. So if Firefox, for example, does not like noexec, we can actually say don't perform noexec, don't enforce noexec just for Firefox, but enforce it for everything else, all your other applications, but just disable it for Firefox. So additionally, if you don't want to use SecADM, there are potential security concerns with utilizing something like a Mac framework. I need to word this very carefully because it's not a vulnerability in SecADM, but it's a vulnerability in the technique we're using in SecADM. So when you deal with the Mac framework, you're dealing with function pointers, an array of function pointers. And if an attacker does get a kernel level exploit to run, he can override that function pointer to point to a malicious code. And so, I mean, if you're in kernel space, you can do a lot more fun things than override a function pointer, but the concept still applies. So if you don't want to use SecADM to toggle those features on a per application basis, you can install that application inside of a jail and turn that feature off just for that jail.
Okay, thanks.
Mm-hmm. Any other questions?
So I had a question about how you're enforcing WXRX. Is that just like a policy decision that you've tried to apply places and make more of your user land only have good mappings, or are you actually enforcing this at the kernel space where, like, if I try to mmap protexec prot_write, it'll fail, or does like malloc return, or does mmap return -1, or do you like kill me, or how does that work?
Mmap returns -1. It's done in the kernel, and it says if this page was created as executable, it can never be the writable flag should never be set. Whether being created with the writable flag or being changed with mprotect. And so let me check on time because I'm allowed to go, and I actually started 5 minutes late actually due to lunch. So pretty much it's in the kernel, and it says it's at create time and mprotect time. So if a page was created as writable, it can't be created as executable, and vice versa. And it can't be changed to map those, to change the protection. If it's created as executable, you can't mprotect it as writable and executable. If it's created as writable, you can't mprotect it as executable. Does that make sense?
That would break lots of, like, pretty much all JIT engines, like, for everything, even in...
Yeah, it's a lot of fun. That's why we have that is precisely why we have the per application toggling of these features. So that in those applications, I run HardenedBSD on my laptop, and I like Chrome, for example, and Chrome will not work with noexec. I've got Pi and Railrow fully applied to Chrome, but Chrome doesn't like noexec. It has to have RWX mappings. And so just for Chrome and a few other applications, but just for Chrome, actually I can show you my rule set. Why don't I do that? Chrome, I've got page exec and mprotect disabled, and for LibreOffice, same thing. For FreeRDP, I've got I'm debugging a bug right now with FreeRDP. I'm working with a FreeRDP developer, so I've got page exec, mprotect, ASLR, and the shared library randomization turned off. For Lua JIT, I've got page exec and mprotect. You get the gist. So yeah, that's it. I would love to take more questions, but I see Rick over there, and I think I might need to give more time to the next presentation. So I will be available the rest of the day until I just go home, because I live just nearby. So feel free to talk to me afterwards. Thank you very much for coming.